Hello again. This video was prepared in order to gain a better understanding of the Job 28.9 concept and the process of constant volume uplift. The Job 28.9 concept was described in a videotape entitled The Job 28.9 Structural Modeling Concept, a Research Proposal. However, the constant volume uplift process was only briefly described. This tape is intended to focus on the uplift process, which is, based upon the concept, the means by which folded mountains are overturned at their root. When studying the process, it is best to begin by investigating how flat beds are deformed by deep crustal uplift. As will be shown, understanding how flat beds are deformed provides the key knowledge necessary to simulate how deformed non-flat line beds are overturned by crustal uplift. Let's begin with a diagram shown in the very first video. This diagram is based on experimental observations in which granular material was uplifted by inflating balloons within a sand-filled tank. Looking at the bottom of the figure, the geometry of the uplifting intrusion, shown in red, is not symmetrical but asymmetrical, with one side significantly steeper than the other. Prior to the formation of the intrusive body, the granular bedding was entirely horizontal or flat line. As the deep intrusion grew in size, the beds were uplifted. Notice that the beds do not curve to match the shape of the intrusive body, but rather form straight line segments. The beds approximate the shape of the intrusive body by varying the length and depth of the individual straight line segments. The diagram at the top of the figure looks at a single bed before and after uplift. Before uplift, the bed is flat line with a uniform thickness along its entire length. After uplift, the bed is segmented into straight line segments. Each segment is related to an original flat line segment by an angle theta, defined here as the shear angle. Notice that the shear angle theta is more or less constant across the uplift. After uplift, straight line segments of the original flat line bed have been moved in space along lines defined by the angle theta. The movement is considered extremely unique in that the displaced line segment remains straight even though the dip of the segment can change. It is the uniqueness of the deformation that defines it. As shown in the next series of diagrams, the deformation mechanism can be described as a constant volume shearing mechanism. Let's begin by dealing with the constant volume aspect of the mechanism. Moving individual bed segments in space along lines of constant dip, theta, is equivalent to changing the shape of a parallelogram such that only two sides of the parallelogram are allowed to change length. The other two sides, dipping at the angle theta, remain constant in length. These restrictions are portrayed in this diagram, which shows three parallelograms, A, B, C, D, A, E, F, D, and A, G, H, D. In each of these parallelograms, only the length of the sides connecting the two infinite line segments changes. Without going into a rigorous proof, this restriction means that each parallelogram has the same area. This area is the same as this area, is the same as this area. This effectively means that for each bed segment, volume is conserved during uplift. The mechanism by which each bed segment is moved in space is similar to sliding a deck of cards. Consider the left diagram as a deck of cards with a mark at each end of the cards. The marks define points along a straight line segment. Sliding or shearing the deck of cards changes the length and dip of the segment while keeping it straight. The total shear strain in the deck is composed of a large number of smaller shear strains. In granular material, the distance between individual shear planes is probably on the order of grain diameters. The previous volume and shearing arguments are depicted in this diagram. Starting with a flat line bed at the top, macro shear planes dipping at an angle theta are projected through the bed, segmenting the bed into 5 segments, numbered 0 through 4. 0, 1, 2, 3, and 4. Here's the macro shear plane. Bed segments are then uplifted, such as segments 1, 2, or 3, or not uplifted, such as segments 0 and 4. Uplifted segments in which the dip changes, such as segments 1 and 3, are deformed along micro shear planes which dip at the same angle as the macro